integrated 3 classes. This week, and really just this week only, we're going to be focusing on some trigonometry unit circle ideas and concepts. So after this week, we're getting into our testing for all students, distance learners, in person. We're going to be starting testing. So this week is just a short unit over some unit circle and trig ideas, just sort of the last couple concepts that we're going to be able to fit in before testing. This is also super useful information for those that are going to take pre-cal next year, or eventually take calculus, or even early or when you go to college, that first math class. So let's go ahead and get into it. All right, so in your notes, let's go ahead and talk about trigonometry a little bit. So last year, you would have taken, or you would have had some trigonometry concepts through your integrated math 2 teacher, and you would remember this as being like SOHCAHTOA, right? That's what you would have remembered this as. Okay, so when we think about trigonometry, what is trigonometry? Well, let's define sort of what it is. Trigonometry is the sort of the study of, or just working with, triangle. This is the breakdown of the word measures. Okay, so what measures are we specifically interested in? Well, there's only 2 types of measures. You have angles, you have sides. That's really what trigonometry is all about. Last year when you were working on this, and by the way, you can write this in your notes. Last year when you were working with triangles, you had something like this, and you have a right angle. A lot of these we're specifically last year when you worked with trigonometry, it sort of branches to any triangle because it's just working with triangles. It's trigonometry. But last year you would focus on a right triangle, and so you had this reference angle theta, and or just basic trigonometry. We're not really going to go back and do any big IM2 review or anything like that. But last year, you would have had the relationship SOHCAHTOA, right? There's special relationships that were found between the different sides. If I were to label this theta is my reference angle. So theta, we'll put this here. This is the reference angle. And definitely write this down, put this example in your notes. You have the opposite side, adjacent side, and the hypotenuse right there. Hopefully a lot of that, you remember doing that. From what students have told me, this is something that you got to right before like COVID shut us down, things like that. So again, we're not gonna do a massive review of this. There's more content that I wanna get to, and in interest of time for this week, I need to hop right into that. But yeah, SOHCAHTOA, I do want to write out those relationships real quick. So I'm gonna do that, and I'm just gonna pause the video and write them out for you guys. These are the different relationships that you would have explored last year, and if you didn't really understand what they were last year, really this is to give a historical aspect. When they were looking at these triangles, and even the Greeks knew about this stuff, they started noticing special relationships between the side lengths of right triangles in relation to this reference angle. So we have opposite over hypotenuse, and they just noticed, hey, there's a special relationship between those sides. Let's give it a name. It's almost like they discovered it and said, okay, let's name it something, and they came up with the word sine. And then the same thing for adjacent hypotenuse and opposite over adjacent. Those comparisons of the sides, they all had a special, like a pattern to them, and they wanted to name them. On your calculator, these just show up as sine. A lot of students say sin, it's sine is how you'd say that. Cosine, right? You want to say cosine, and then tan is tangent. Okay, those are the main ones. There's a lot more, and we're going to get to these later on in the week, these other 3. If you're taking pre-cal or calculus next year, those will come up. But for now, that's really all we're going to do as far as review. I'm going to draw a line in our notes, and we're going to talk about special right triangles. Okay. We've got a couple special cases of right triangles, and from what I've heard from students that I've taught in person this to already, they said that they don't really remember talking about this that much. Okay, maybe I had one or two that were like, oh yeah, I remember that. So we have two types of triangles that we want to draw. So let's go ahead and draw ourselves some right triangles. Good as you can. Mine's not very good, but that's fine there. Two types. It needs to be a little bit longer on the hypotenuse. Right there. Okay. Now we're going to add some angles in here. This one's going to be 45, and as well as the other one here. So make sure you're drawing these in your notes. This one is a 60 degree, and this one is a 30 degree. And then of course these are right triangles, so we're going to put the right angle in the this corner here. There we go. Okay, so we've got these special right triangles, and they have names. This one here is a 45, 45, 90. Okay, that's representing the angles. This one here is a 30, 60, 90. Again, it's from what I've heard, it's unlikely that you remember this. That is okay. That is okay. So there are some special relationships. Let's go ahead and talk about Delta Math. Let's pull up some problems from Delta Math that are going to involve these questions, or these special right triangles. So here is the different sections. This is only going to be this week's assignment. I really don't think I'm adding any more to it, but this is due by Friday. So Friday the 9th. Make sure that you get that. But we're going to talk about these ratios of special right triangles, and I'm going to find a 45, 45, 90 triangle. Okay, so this one's fine right here. So if we wanted to answer this, we could of course use SOHCAHTOA to help us out. But the purpose of this lesson is to describe some more of the special relationships. And this is trigonometry. We're studying the measures of the angles and sides in trigonometry of these special triangles. So these have special rules to them. Okay, so we're going to label some of these sides here. There is a special relationship after, and you imagine it the same way that these were created, sine, cosine, tangent. They were just they discovered a pattern over time. There are special patterns within these triangles as well. First off, for the 45, 45, 90, you have, and we're going to call our hypotenuse in this case S here. That's going to represent like just the side length of it, whatever that length is going to, we're just going to call that hypotenuse S in this case. Now they've noticed a relationship that this side over here, this leg S, this leg over here is going to be S, or the hypotenuse, times square root 2 over 2. Okay? S times square root 2 over 2. That's what they figured out, that relationship. That's going to help us solve a lot of questions. I'm trying to draw an S. I can't do it. Whatever. Now, we also want to talk about this. Important for these 45, 45, 90. This is an isosceles right triangle. So we're going to say this. Both legs of the right triangle, or of the 45, 45, 90 right triangle are congruent. And we would call it an isosceles right triangle. So anytime you see an isosceles right triangle, it has to be a 45, 45, 90 triangle. So what does this mean? What's going to go down here? Well, the exact same thing is up here. It's the same relationship. S times square root 2 over 2. All right, so this is in fact very helpful for us to solve these problems. Okay, so let's look at our example. I'm going to pull up Paint here, and we'll get our Delta Math up, and we're going to work this question here. And you'll notice this here, it has to be in radical form with a rational denominator. So I can't use decimals here. That's important. That would make this a lot easier if we're allowed to use decimals, but we're going to practice using radical form with a rational denominator. Okay, so we have this rule. Pull up Paint again. Okay, so we have these rules here, and we know that we have this length square root 3. Make sure that you've written this example. So underneath the 45, 45, 90, put an example. And we're going to draw this, and we're trying to find the missing leg. Well, what do we know about this? Well, we know that this is our this is our side length that is, that's what we're going to be using in an equation. But we know that this missing value has to be equal to this times square root 2 over 2. So it's square root, so we have square root 3. Barely see that. Hold on, let me make it a larger brush. So square root 3 times square root 2. Okay. That's what we need to do to answer this question. Now, the good news is we don't really have to do much algebra here. We just took the hypotenuse and plugged it in, and we didn't have to use any of our trigonometry, like cosine, sine, or tangent with these special right triangles. These are the kind of relationships that we were trying to discover today. Now, do you remember how to do this? Like, what does this actually mean? How do we multiply these radicals? Well, hopefully this is okay. It's going to be equivalent to this square root of 3 times 2. Hopefully that's okay. And maybe you didn't know that rule for radicals when multiplying them right here, but that is going to be how that works. Anytime you're multiplying two square of the same root, they have to be the same root. Anytime you multiply two that have the same type of root, you can just multiply their values together, okay, inside of the root. So this is going to get us square root 6 over 2. And that's going to be the answer to this question. Now this one is a more straightforward. Some of these can get pretty complicated. So we are going to type this in though. So it's going to be square root 6 divided by 2. And that should work. Okay, we did it. Now they have other ways of doing it in Delta Math. I mean, it ended up being the same thing mostly. They have something called rationalizing, which we're going to have to deal with in a second. So let me find us another example to look at. All right, so this one is going to have a few more complications to it, a few more things to look at. So we are going to work this one. So let's draw this example under our 45, 45, 90 triangles. Let me just create a new file here. New, don't say. Okay, there we go. So we've got our new problem here, and we're still using the same exact relationship here. We're trying to find this though. We're trying to find our hypotenuse. We don't know what it is. We're trying to find that, okay? But we do know that whatever this is, if we call this, like in our example, we call this S, right? We know that this has to be S times square root 2 over 2, right? That has to be the case. So I can actually replace this letter. I'm going to put actually an X there. I know it's kind of confusing how I'm using these variables, but I'm using like S and X and stuff like that. But this S over on the left over here is just supposed to represent a side length. It could be anything, okay? But in this problem here, they're saying, okay, it's well, it's the unknown. It's what we're trying to find. But we know this has to be true here based on this. This side has to be equal to this one, but we have to multiply this side, or this part here, by square root 2 over 2. So now we got to get some algebra involved. So I'm going to shift this over here, okay? We're going to solve this. What would we want to do first? Well, we're just trying to get x alone, so I'm going to multiply by 2. This goes away, so times 2. That gets us, I'll write in black, 2 square root 3 equals x times square root 2. All right, now we almost have x alone. We just need to divide square root 2 from both sides. And this should give us our answer. However, there is a problem. Okay. If I try to type this in here, if I tried to take that answer right here and type that in, there's a problem because it's this. We do not have a rational denominator, and that's what we have to have. So in your notes over to the side, I would like you to write out this term rationalizing. Okay? What rationalizing means is to eliminate, or I'll say remove the irrational number from the denominator. Okay. That's what rationalizing means. Okay. So we've got I'm going to give an example. So add this to your notes. Example EX, right? Let's say that we had a fraction that looked like this. Just something simple, right? Square root 1 over square root of 1/2. 1 divided by square root of 2. So this would be an irrational number on the denominator. So to rationalize it, okay, change the color. To rationalize it, we are going to multiply top and the bottom by that rational number on the bottom. So this is square root 2. This is square root 2. Okay, on the top and bottom. Really, if we hide, let me get rid of this. Let's hide this for a second. What is square root 2 over square root 2? Well, it's just a 1, right? We're really just multiplying this red number by 1. That's all we're doing. We're not really changing anything. We're just manipulating its form. So let's talk about what happens here. When you multiply fractions, you multiply straight across. This becomes square root 2 over square root 2 times square root 2. We've already seen an example where we're multiplying these radicals. So what does that become on the bottom? Well, it becomes square root 2 times square root 2 times 2. We actually multiply. Remember, the radicals, those rules for that are to multiply them together. This becomes square root 2 over square root 4. And then finally, this becomes square root 2 over 2. So all we did was move this to the top, and really we just got rid of the square root on the bottom, and it just became a 2. So that would be an example of rationalizing. So over here, the example here, to get this square root out of the denominator, we are going to multiply by, well, it's whatever's on the bottom. It's just whatever irrational number is on the bottom. So we do square root 2 on the bottom and the top. So that is going to change our answer. That's going to make it, what did square root 2 times square root 2 end up becoming? Well, and I'm going to go ahead and, you can shortcut a lot of this. It becomes square root 4. Up top, square root 2 times square root 3. This becomes 2 times square root 6. We've seen these before already today. What is square root 4? Well, it's 2 on the bottom. Square root 6. A little bit more. Now these 2's here are going to divide away, and so it simplifies a little bit further. And that means our answer is square root of 6. Okay. So that's a lesson on what's called rationalizing. In my opinion, it's not the most necessary thing. I don't know why mathematics enjoys rationalizing or why it's necessary, but a lot of big tests are going to expect that you rationalize. Those that are going to take a entry-level math class in college, this is very common to see rationalizing in some of the content. So this is something that is very, very likely you'll see it again at some point. okay? If not next year, your senior year, if you're taking stats with me. We don't really do that a lot. I don't think at all. But if you're taking pre-cal, absolutely. Calculus, absolutely. Or college algebra, if you're doing dual enrollment, it's very likely that'll pop up. So the answer is square root 6. Okay. All right. There we go. I want to find one more that we're not really going to work. So this one right here, this one does not require calculation if we look at it. Because we wrote down this rule, both legs of the 45, 45, 90 right triangle are congruent. So this leg is congruent to this one. So when I look at this problem here, this 7 should be equal to this. So the answer is 7. So those are really nice problems to have to do, okay? All right, perfect. So now, let's go ahead and we'll finish up this lesson by talking about the 30, 60, 90. So for the 30, 60, 90, we're gonna put the S here. And that side length is always going to be opposite of the 30-degree angle. So we're going to put another bullet point, and we're going to say the side opposite of the 30-degree angle is always length S. Okay? That's going to always be true for these 30, 60, 90s. They have the, that's the length. So just like we did with the hypotenuse over here, this one is going to be our length S here. All right. We don't necessarily need to relate these directly to each other. So we kind of want to separate those. This is like its own setting. Don't put this S with that one over there. Don't mix those up. Okay. Just to help us keep track of how these side lengths relate, which there's a really nice relationship with a 30, 60, 90 in the fact that the hypotenuse is double this length here. And that should make sense if we think about how this angle's 30, this one's 60, it's double, right? And there's a relationship there. That's what they found when they discovered these, okay? That's a pretty simple relationship. That can help answer a lot of questions. And then the last part over here, this side length is the same, except I have to multiply it by square root 3. Okay. The reason all of this is important that we're talking about this is going to help us a lot when we start building this unit circle. So that's what we're going to be working on the rest of the week. Okay. But here are the rules that we need for this. Okay. Let's work some problems. Let's put some examples down for this. All right, perfect. So we're going to go ahead and do this problem here. So this one, go ahead and draw it. We don't really need a lot of, this one is not going to require a lot of work, okay? Save, because we have that very handy rule about this hypotenuse, and we have the hypotenuse here. When we look at this, for a 30, 60, 90, we know that this equal to 2 times this side length, if we're calling this S and not X, right? So really all this means is I just need to divide 5 by 2. If I'm doing the algebra here, let's move that over. Move that up. I'm just going to divide both sides by 2. All right? All that means that I need to do. And that gets us this. So this is 5 over 2. I don't know if a decimal would work here for an entry of an answer, but I'm just going to put 5 divided by 2, and we get it correct. Okay. Another one. Let's get one a little more complex. This should be pretty good. This is probably one of the more complicated ones that you'll see for a 30, 60, 90. 30, 60, 90s are typically going to be a little bit easier to solve. But let's go ahead and work this one. Okay, so here's this one here. Write that one in your notes. So we know that this side here is equal to this one if we called this S, right? S. We know that this side has to be equal to this one, except it's multiplied by square root 3. Okay? That's all that we're saying here. Okay? So it's this side length, but we multiplied it by that. So all I need to do is divide by square root 3. needs to happen. And so that gets us square root 7 over square root 3 equals s, or if you want to put x, I'll put x here, right? Because that's, sorry, hopefully that's not confusing anybody too bad as far as keeping track of these values. We're trying to find this length here. We can call this x if we need to, right? That is what that length is from our notes over here. We almost have the answer, except we can't, this would be the answer, except we can't write it like this, right? We can't type that into Delta Math. It will not work. We have to rationalize it. So what do I multiply by on top and bottom? Well, that's going to be whatever that radical is on the bottom. So it's square root 3 over square root 3. That's going to help us. This is going to get us square root 21 on top. Remember, you just multiply inside. Square root 9 on the bottom equals x. And I'm just going to write over here. It looks like my camera's in the way. There we go. Hold on. Square root of 21, that's not a perfect square, and it cannot be simplified. We haven't seen any problems where we've had to simplify yet. You probably will run into that, where you have to simplify, get the radical to its simplest form. I'll try to do one more example where that happens, but and to finish things up here. But let's go ahead and this is going to be square root 21 over 3, and that should be the answer. So square root 21 divided by 3. We got it. All right, let me find an example that we're going to have to do a little more rationalizing, where we have to simplify as well. Okay, it took me a little bit, but I did find one that's going to work for us. So we have this example here. This will be the last one of this video. So let's go ahead and write that down. There are 30, 60, 90 special right triangle. And when we look at our rules for this, we know that this has to be equal to this side length here. So we'll just go ahead and put an x here, by the way, times square root 3. Then how we solve this is we are going to move this down there, and then we're going to divide square root of 3 here, okay? And so that's going to get us a value that we're going to have to rationalize. So I'll go ahead and move this over a little bit. Square root 3. Okay. And so to rationalize, we're going to do times, and I'll use the blue values again. So times square root 3 top and bottom. And what that's going to get us is that's going to get us, this is going to be 18 over here. So this is 18 on top and 3 on the bottom. Now, if I type this in, it will be wrong as well because we have to simplify. So there's two methods that people or students remember mostly from last year. There's something called the birthday cake. I know Von Dolan taught that. Delaney or Ruttencutter taught that as well. However, I know Coach Hammond didn't do that way. And I don't really know much about the birthday cake method. If you remember the birthday cake method, you can use that. But I know somebody said something about you got to get a candle at the top. That's the one or something like that. But we're going to be doing it this way. So if we're in Coach Hammond's class, you'll remember this method to be familiar. Apparently, he had a story with it about. Which I'll bring up in a second, but we take the square root of 18. We got to simplify that radical, and what we do is called the prime factorization, which is we get this into its prime factors. So what are the prime numbers that compose this 18? Well, 2 is a prime number, but 2 times 9, right? And then 9 has prime numbers 3 and 3. So apparently the story was you had to have like a partner to leave the house or something, but one of them doesn't come back. Not really sure. Anyway, let me describe it the proper way for those that might be confused by that. Every pair, we don't really care about these numbers anymore because we've broken them down into the primes. 2 times 3 times 3 is the original number. So the 3 and the 3 here, they are a pair. So for every pair, we're going to pull that outside of the radical. Anything that's not a pair stays behind. So This is going to become, up top, the square root 18 becomes 3 times square root 2. And on the bottom, we put the 3. So this is actually what our value is. Now, you'll notice that these 3's can cross through those because they'll simplify. And our answer to this problem is square root 2. That's the actual answer. So we pull up Delta Math, square root 2, submit, and that's going to give us the right answer. Okay, so hopefully that's not too confusing, and maybe you remember doing that, especially those in Coach Hammond's class. But you will run up upon a couple questions like that. So if you're confused as to why you might have missed them because you didn't simplify here, then that's probably why. If you need extra practice with simplifying these radicals, please reach out to me and let me know. I can give you some just very simple problems to work to get better at that, but it is something you're going to need to know how to do. Maybe you dodge all the ones that have that. You only have, I think, 8 questions here, so maybe you don't have to worry about it too much, but I know it's a skill that is important, and you would have learned it last year with that birthday cake method or with what I did that you did in Coach Hammond. So anyway, we're going to stop the lesson here. Probably going to have another one up tomorrow talking about unit circle, so just stand by for that. I'm going to go ahead and end it.